Okay, on to chi-squared test number 2, and this is the chi-squared test for independence. So it's looking at sets of data and deciding whether or not two factors are independent of each other. But before we move on, I want us to have a little bit more practice with this null hypothesis and alternative hypothesis thing. So imagine I go out and I collect a sample of shoe sizes from all the pupils in the school. So I've taken a sample of the whole population. And I'm going to analyse it using the chi-squared goodness of fit model, the one that you've been doing for the last few days. So I'm going to look at it and use the chi-squared goodness of fit to decide whether my sample fits with the expected for the population, whether my sample represents what you'd expect from the whole population. So first of all, I'd like you to write the null hypothesis and the alternative hypothesis for this test. Once you've done that, looking at this table, I got this value here for my chi-squared test. Should I accept or reject my null hypothesis? And what does this mean about my sample? So pause the video here, write your null hypothesis, alternative hypothesis, say whether you're going to accept or reject your null hypothesis, and tell me what that means about your sample. Okay, so you should have written the null hypothesis that there is no significant difference between the sample of shoe sizes at school and the expected shoe sizes of the population. The alternative hypothesis then would be that there is a difference between the sample shoe sizes in the school and the expected population of shoe sizes. Obviously, we'd expect in the population that there would be lots of people with medium-sized feet, a few people with small feet and a few people with large feet. If I get this chi-squared value here, because it is not in the last two columns, there is a greater than 5% likelihood that any differences in my data, any differences between my data and the population, are due to chance alone. So if I do see any deviations from what I expect, they're likely to be due to chance alone. So this means, because it's in this column here, I would accept my null hypothesis. And what does that mean about my sample? Well, it means that it's representative of the population. It means it's pretty much what I'd expect. Obviously, the further this way you go, the more representative of the population your sample is. Okay, so we're going to move on to look at this independence test now. Your homework for this week is to complete the exercise 5H on pages 238 to 241, all of the questions. I'd like you to do one of the questions in the long-handed way that we're going to do today, and that's it. Next lesson I'm going to teach you how to do chi-squared, this kind of chi-squared, using your calculator. All the rest of the questions you can use your calculator for. So just one question needs to be done in a long-handed way. Okay, so the independence test is used to see whether one factor affects another factor. So in this example that I'm going to give you, we're going to test whether gender affects the level of education that a person receives. So we're looking at whether or not the gender of a person is independent to their education level. If it is independent, we would expect to see the same number of females and males, or similar numbers of females and males, in all of these columns. If it's not independent, we'd expect to see more females in some of the columns and more males in others, showing that gender does affect the level of education, or that gender is dependent on the level of education, or the other way around. Education is dependent on gender. So this table here is called a two-way contingency table because it holds two different variables. The first variable, gender, and the second variable, level of education. The totals along here tell us, this one tells us how many females there are in the study. This one tells us how many males there are in the study. Then we've got totals along the bottom here. So we've got the number of high school educated people, the number of bachelor's educated people, that's undergrad, the number of master's educated people, and the number of PhD educated people. Then here we've got them all added up together, and that gives us the total number of people in the study. So that would be adding this one and this one together, or this, 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 and this. Not adding all of these and all of these, because then you'll double up on the number of people. So it's important to know what those totals mean, because we are going to use them quite a lot. Okay, so we're going to find out whether your gender affects the level of education you receive. How are we going to do that? Well, first things first, obviously we have to write our hypotheses. Now we need to be a bit careful because this changes now, because we're using a different type of chi-squared test. The null hypothesis is that the factors in the experiment are independent of each other. So if I was going to write this for my current example, I would say my null hypothesis is that the level of education you receive is independent, that means not affected by, your gender. The alternative hypothesis is that the factors in the experiment are dependent on each other. So my alternative hypothesis for this test would be that the level of education you receive is dependent on your gender. So that would mean that the education that you receive depends on what gender you are. So then we take these hypotheses and we take this table and we go through the chi-squared test, and we're looking to see whether we accept or reject the null hypothesis, just like before. Okay, so these are our observed values. I have collected some data on a group of 395 people, and I have my observed table here. Now, it is not going to be as straightforward calculating the expected values for a two-way table. That's because I have a different number of females compared to males. So I can't just evenly spread these numbers all around the table. I have to take that into account. I also have a different number of high school educated, bachelor's educated, master's educated, and PhD educated people. So again, I can't just evenly spread these numbers like we were before. I can't take that 395 and say, right, I need to spread it evenly between these 8 boxes. It's not going to work that way. So in this case, when we come to calculate the expected, we use the totals. So let's imagine I'm trying to calculate my expected number of females who are high school educated. First things first, I go across and I look at this total, 201. I had 201 women in my study. I'm going to multiply that by this total, 100. That's how many people were high school educated. So I do 201 multiplied by 100. I'm then going to divide that number by the total number of people in the study, 395. And that will give me my expected value for the number of female high school educated individuals. So what I'd like you to do is just write out this table first of all. This is your observed table. Then create another table, exactly the same, but calculate the expected values. So work out what the expected values for each of these boxes are. Pause the video here. When you're done, carry on watching and check and see whether your expected values are correct. Okay, so here is our observed table. And I'm going to uncover in a second the expected values here. And we'll see what we get and whether or not you've got the same expected values. So don't forget, for this box here, I would multiply this total by this total. For the male box here, I would multiply this total by this total. So let's see what you got. You should have 50.886 for high school educated females, 49.114 for high school educated males. We then go on to 49.868 for bachelor's females and 48.132 for bachelor's males. 50.377 for master's females and 48.623 for master's males. And finally 49.868 for PhD females and 48.132 for PhD males. These are the expected values if they were evenly spread throughout the groups according to how many males and females we have and how many of each of these different educations we have. Then we carry on and we calculate the residual squared, and then the component, exactly the same way as you did before. But all of your tables are going to look like this, just without the totals on. You don't need the totals for the next few tables. For the residual, remember it's observed minus expected. So your residual table should have whatever the observed value is minus whatever the expected value is for that group. Then you square it, so you have another table where you square it, and then you divide by whatever the expected value was, and you have another table for that, and that's your component. So here we go, you should end up with 3 tables like this. This last one here being the component. And then you add all of those values together at the end to give you your chi-squared value, just like you did before. So pause the video here, draw out your tables and see if you can fill in those boxes. Okay, lovely. Check your answers and see if you got the same as me. Once you've added them together, you should get a chi-squared value of around 7.61. Now this entirely depends on how much you rounded these figures as you went along. You might find that you get a slightly smaller number or a slightly bigger number, but it shouldn't make too much difference. So we're going to take this chi-squared value and I'm going to round it to 7.62. And I'm going to take it across to our table. Now, remember we need the degrees of freedom. this is a little bit different because suddenly we have more than one set of categories. So let's go back and have a look at how many categories we have. We have 1, 2, 3, 4 types of education, and we have 2 genders. So what I'm going to do to give me my degrees of freedom is do the 4 minus 1 multiplied by the 2 minus 1. So I end up with 3 times 1. So my degrees of freedom in this case is 3. So I'm going to go back to my table, find my degrees of freedom, 3, and I'm going to shimmy across like this until I get to the closest value to the one that I calculated, 0.05. So remember, if we land in this column here, it means that there is a 5% likelihood that the differences that I've seen between my observed values and the expected values are due to chance alone. So what that means is there is very likely a difference between the observed values and the expected values. It means that I have to reject my null hypothesis. I have to say that actually gender does affect the level of education that people get. It seems that level of education is dependent on gender to a certain extent. And if we just go back up again and compare our observed and expected, we can sort of see this. Because if we look at the PhD here, we would expect there to be an almost equal number of males and females being PhD educated. But actually when we look, there's this enormous difference between them. So it's clear that in this case, the gender, whether or not someone is female or male, has affected whether or not they get a PhD education. The same is true here. We would expect an almost equal number of males and females to be bachelor educated. But actually, when we look at the values, far more females are bachelors educated than we would expect, and far fewer males. Now that is probably because those males have now gone on to become masters or PhD educated. So in this example, we have to reject our null hypothesis, we have to accept our alternative hypothesis, and we have to say that the level of education is dependent on gender. Gender does influence the level of education. Okay, your turn then. A group of students in grades 4, 5 and 6 were asked what the most important part of school was. I would like you to work out whether or not the age of the child affects their perception of the most important part of school. So these are the 3 options they were given. They could either say that grades were the most important, being popular was the most important, or doing sports was the most important. And they were asked in grade 4, in grade 5 and grade 6. And this is how many students gave that response. So start off, you need to write your null hypothesis and you need to write your alternative hypothesis. Please be very careful with the wording. It must include the words dependent or independent. So if you can't remember, flick back to that bit of the video and remind yourself of which way round it is. Then you need to work through those tables. You need to create yourself an expected table. Don't forget to do that. You're going to need to put some totals on this observed table. Calculate your residual squared, and your component. Collect your chi-squared value work out your degrees of freedom and go to the table.